Hello, everybody. Welcome to my kitchen/classroom again for the 5th week. So I understand that recently you've been loaded with a lot of information regarding how to distinguish among those 4 major type of reactions that are S1, E1, S2, and E2. So instead of loading you with more information today, I'm going to pause a little bit and go back to what Sydney and Samantha talked about this Monday and rehash some points and maybe answer some questions. And then if we have time left over, we're going to do some practice problems together from homeworks or study group sheets or exams, whatever you like. Anyway, so it seems like most people are here already, so I'm going to get started. And today I'm going to be on the board because I anticipate people to ask a lot of questions and I cannot draw on my computer because I don't have a tablet. All right, so distinguishing among 4 reaction types. So the first thing, can anybody tell me what we should look at when we see a reaction and we're trying to figure out what exactly to do?
The substrate?
The substrate, yes, thank you. Okay, so the first thing is the substrate. Feel free to look at your notes. This is not a test, so feel free to go back to your notes. I don't know if you can see whatever I wrote. Can everybody see? Okay, if you can see, I'm gonna move the computer closer and keep up with that. So, in terms of substrates, we're going to consider the number of carbons attached to the carbon center that we're interested in. So there are 3 types, well, actually, there are 4 types of carbon centers, but we are only concerned with 3 of them. So primary, secondary, and tertiary. Primary means there's only another carbon attached to it. Secondary means 2. Tertiary means 3. So for primary carbon, what kind of reactions are most likely to occur? No, we have
SN1 and E1.
Oh, there you go, Emma. Thank you. You said what?
SN2.
SN2 reaction. Yep, that's true. What else? SN2 is correct.
Reaction.
Sorry, you cut off.
Oh, the E2.
The E2 reaction. Wonderful. So why is that? Why can we not do SN1 or E1 reactions with primary substrates?
Because then it'll be too unstable.
Then it would be too unstable. What would be too unstable?
Or like the carbocation.
The carbocation, yes. So for SN1 and E1 reactions, what we remember from those reactions is that the first thing that happens is the departure of a leaving group and the generation of a carbocation. And if you have a primary carbocation, it's going to get very ugly very soon because they don't want to exist at all. Okay, good. So what about, I'm going to leave the secondary because that's like muggy water part. How about tertiary? What kind of reactions would prefer to happen for tertiary carbocations or just tertiary carbon centers?
SN1 and E1.
SN1 and E1. 1 and E1. Okay, sounds good. What about secondary? Can we rule anything out with the secondary carbons?
No.
Somebody is shaking their heads. Karina, were you saying something?
No, because they're like, if you're looking at a Venn diagram, they fall in the middle in terms of it could possibly be either one, so you can't rule anything out.
Yep. You're absolutely correct. So secondary carbons are the annoying ones because we cannot rule anything out just based on the substrate. So that's okay because we have 2 other things to look at in terms of determining what kind of reaction would happen. So the first thing was substrates. Any questions so far regarding how to distinguish between the types of substrates? If not, we're going to move on to the next thing, which is solvent. All right. So number 2, we have solvent. So let me ask you guys a question. Is everybody clear with what it means to be a protic solvent, a polar protic solvent, if you remember from your previous lecture. Because understanding this is going to be very important for understanding what I'm going to show you next. Since nobody's talking, I'm going to just re-go over this just in case somebody has a question but really doesn't want to raise their hand. Okay, so protic solvent, or I'm going to add the word polar in front of it because polar solvents are the solvents that we carry out those 4 types of reactions in. So polar protic solvents means that you have an acidic proton, acidic H. So what's an acidic H? Well, an acidic H is an H attached to an electronegative atom, such as oxygen or nitrogen. So some polar protic solvents are, I'm going to give you some examples. Water, OH, H. Oxygen is very electronegative. When you have H's attached to oxygen, you have a polar protic solvent. And if I draw the dipole moment, it's going to look like this. Okay, so in addition to water, anytime basically you see an OH, that is a polar protic solvent. We can say ethanol, ETOH, same thing, or methanol, or whatever. So these are polar protic solvents for you. And last class, you learned that polar protic solvents favor elimination reactions. Does anybody remember why it favors elimination reactions instead of substitution reactions? I'm going to give you a sec to flip through your notes and, you know, have a discussion with yourself in your head. If you feel like talking, feel free. If you don't feel like talking, that's fine. I'm just going to re-go over the point. I'm just going to sit here until somebody tells me to move on or suggests an answer. Jeremy, what do you think? Jeremy's not answering. Okay, Nestor, what do you think? Since you have your camera on and I know you're listening.
I don't know, just like maybe because it could like give away an H or something.
Maybe it can do what? You're onto something very important. I just want to make sure I hear you clearly.
It's like give away an H.
You're absolutely right. So polar protic solvents can give away H. How is that? How the hell is that important? Well, okay, so let's consider the difference between an elimination reaction and a substitution reaction. So for substitution reactions, the most important reagent would be the nucleophile, which I draw like this, just Nu with a negative charge. That's my shorthand for a nucleophile. Okay, so nucleophiles are mostly with negative charges, or if not negative charges, they're weak nucleophiles. And the more electronegative the nucleophile is, the more hydrogen bonding there is with the solvent, because the solvents, remember, they are basically solvents with acidic protons, which are capable of hydrogen bonding. So what exactly is hydrogen bonding again? Well, basically, you have, for example, I'm going to draw water, right? I'm going to draw another water. And see, the oxygen has 2 lone pairs. They're very negative. And we have partial positive on the H's. What's going to happen is that the lone pair on the oxygen is going to try to grab onto the partial positive hydrogen, hence hydrogen bonding. And let's think, if I replace my water with a nucleophile, such as, somebody give me a nucleophile. Just shout out a name for a nucleophile.
Yeah.
What?
CN.
CN? Sound good? All right, we got CN. CN minus? CN minus. Great. So we have a negative charge, a hard negative. And now we have a bunch of water surrounding it. What do you think is going to happen with the minus charge on the C? Is it just going to sit there and chill?
The partial positive charges from the H would be attracted to the negative charge on the carbon.
You're absolutely right. So imagine we're in a sea of water, and now we have a negative swimming in the sea. And what's going to happen is that all the positive H's are going to be attracted to the negative charge. So you're going to end up having a bunch of H's, a bunch of H's, H's, surrounding this part that was initially meant for attacking an electrophile. So do you think it's a good thing or a bad thing for the reaction that's meant to happen?
Good thing.
It's a good thing. Why?
Well, the reaction occurs when molecules collide and bond. Like
You're
that.
absolutely correct. Yes. However, in this case, we're trying to do a substitution reaction. So we want our nucleophile to collide with our electrophile. But now our nucleophile is surrounded completely by irrelevant water, which does not participate in a reaction. So is it a good thing or a bad thing for the substitution reaction?
Bad.
It's probably not so great, right? Because imagine you're trying to mop up your floor, right? You got some crap on your floor and you have this mop, that's wet mop, you're trying to, mop it up. However, I'm going to put a plastic bag outside of your mop and say, wipe up my floor without taking off the bag. Well, here you go, wiping the floor, and you're just going to make it worse because you have a plastic bag surrounding the wet mop that I'm going to use to interact with my dirty surface. Therefore, it's the same concept. Here you want to attack with the negative charge. However, you have a bunch of polar protic solvents that are interfering with my negative charge. Therefore, it's going to become very, very difficult for a nucleophile to go ahead and initiate an attack on an electrophile. So, CN is a very good example. I would like to talk about some trends. So we all know that the halogens a lot of times are used to illustrate periodic trends. So here I'm going to draw a bunch of halogens on the board. F minus, Cl minus, Br minus, I minus. From the smallest to the biggest. Now, jog your memory and I'm going to ask a question about GenChem. Which one of them is the most electronegative?
Fluorine.
Fluorine is, yes, thank you, Lizette. Fluorine is the most electronegative. So, which one of you is going to participate in most hydrogen bonding? It's most electronegative. So, some of them, one of them has the strongest hydrogen bonding. Which one is it? Is the one that's most electronegative or the one that's least electronegative?
Most.
The one that's most electronegative. Thank you, Karina. The one that's most electronegative is going to participate in the most hydrogen bonding because it's the biggest delta negative and it's going to attract the most delta plus. So, if we're in a polar Protic solvent, the more electronegative you are, the more hydrogen bonding it will occur on you, and the less nucleophilic you're going to be. Therefore, in this column of periodic table, nucleophilicity increases. as electronegativity decreases in a polar protic solvent. So pay attention to polar protic solvent, because that's not necessarily true when we switch to a different type of solvent. So it only applies in this situation. The nucleophilicity would increase as your electronegativity drops in polar protic solvent. Okay. Questions so far? So this is the reason why polar protic solvents do not favor substitution reactions. You're throwing a nucleophile, it's going to be surrounded by a bunch of hydrogen bonding, and your nucleophile is therefore pretty much dead in terms of its nucleophilicity. It can only pretty much act as base. Even though it's a crappy base, it's better than no reaction at all, and it's going to try to go ahead and have an elimination reaction instead. Okay. Questions so far? If not, I'm going to move on to the next point. Okay. Doesn't seem like people are confused by anything. So hopefully as I move on, everything's still going to stay clear in your head. Okay, so we just talked about polar protic solvent. What about polar aprotic solvent? We know what polar means. What about aprotic? What does that mean?
It doesn't donate a hydrogen.
It means, sorry?
It doesn't donate a hydrogen.
It does not donate a hydrogen. You're absolutely right. So polar aprotic solvent means that in the solvent, you don't have hydrogen bonding occurring. It does not mean, however, that you do not have any hydrogens. It means that you do not have a hydrogen that is attached to an electronegative atom. So I'm going to give you some examples of polar aprotic solvents. For example, we have this, acetone. Acetone. We also have something that looks very similar to acetone and you've already learned about, which is DMSO, dimethyl sulfoxide. Dimethyl sulfoxide. Okay, what else? Well, we have acetonitrile, which looks like this. We have a CH3. We have a C triple bonded to a nitrogen. This is acetonitrile, or DMF. Something you will encounter definitely in the future. So I'm just going to draw it out for future reference. This is, oh no, missing a hydrogen. DMF, dimethylformamide. Just in case you couldn't see. Okay, so polar aprotic solvents. I'm telling you that they favor substitution reactions over elimination reactions. And based on what we just talked about, can you guess why it can favor substitution reactions? It has something to do with hydrogen bonding, or the lack thereof. I don't know. Let your imaginations run wild.
Is it because there's no hydrogen bonding that means there's no anions with stabilization so they can react?
You're absolutely correct. Thank you, Arifa. So we're in polar aprotic solvent, which means that we cannot conduct hydrogen bonding. That means that our nucleophile, if it's a strong nucleophile, it will stay a strong nucleophile. If it's a weak nucleophile, it's still going to be a nucleophile. You know, nobody's going to come in and surround it and hinder its ability. So for polar aprotic solvents, if we look at the same series of nucleophiles, F minus, Cl minus, Br minus, and I minus, in polar aprotic solvent, nucleophilicity increases in the reverse order, as we just talked about. So increases the other way. more electronegative it is, more nucleophilic it is in polar aprotic solvent. Any questions so far regarding the two different trans that we just talked about? No questions? Okay, cool. I'm going to leave it here for half a minute, just in case you need a little more time to copy it down. And if you're done, I'm going to move on to the next thing, which is a little more difficult. Okay, so it seems like people whom I can see have their heads up. So I'm just going to trust that everybody has the information down. Okay, so we just talked about substrate and solvent, and the last thing I want to talk about, which is where the most mess comes from, that is the nucleophile versus the base, the attacking molecule, as Sydney and Sam put it. The attacker. Acid, nucleophile versus base. So for substitution reaction, do we need a nucleophile or a base?
A nucleophile?
We want a nucleophile, right? So the stronger it is, the better, obviously. And I'm going to give you a bunch of examples, which Sydney has already showed you, but I think it would be good for me to re-emphasize them. A bunch of molecules that can only act as nucleophiles, such as SH minus, H2S, what else? Cl minus, Br minus, I minus. Let's pay attention to the last three. They're halogens. Why do you think they cannot act as good bases? They have minus charges. So what's the problem? How do we even determine basicity? Learn from Jenka, by the way.
Well, bases deprotonate the acid in solution, so maybe the Cl minus, like the halogens, like being alone more than they like deprotonating.
They like being alone. Why do they like to be alone? You're onto something very important. So what's the other form? If they're not alone, what would they be with?
I mean, HCl, HBr, HI, they're all strong acids, and I mean, in water, they don't stay together, they dissociate, so.
You're absolutely right. So HCl, HBr, HI, they're all very strong acids. Therefore, if you put them in water or some other solvents, they would prefer to fall apart. And it would be very difficult for Cl to grab another H and say, I'm just going to hang out with this H. I'm never going to fall apart. That's probably not going to happen unless you have a bottle of pure HCl. In that case, your H and Cl are probably forced to stick together. Every time you're asked to determine basicity, think the conjugate acid. If it's a weak acid, then the base must be a strong base. But in this case, it's the reverse. The conjugate acids are all very strong acids that you'll learn about in Gen Chem. Therefore, those bases are terrible bases, and they can only act as good nucleophiles. All right. What about for elimination reactions? What kind of reagents do we want to use? Are they nucleophiles? Are they bases? Or does it not matter?
Strong bases.
We want strong bases. Thank you. So, strong bases. I'm going to give you some examples. Terbutoxide. A lot of times you will see terbutoxide written like this, or sometimes you could see the counter ion as well. So I'm going to give you a common counter ion, which is potassium. If it's written this way, it means that the terbutoxide is the active part, whereas the potassium is just a spectator ion. Okay, what else? Well, we have a bunch of very strong bases that are hydrides. NaH, KH, cannot even write. NaH and KH. So they both have H's, but those H's are very special. They're not H pluses, they are H minuses. So if you see NaH or KH, the H minus is the active reagent, whereas the sodium plus or the K plus are spectator ions. And the H's are very small, they're very concentrated charges, therefore they're excellent bases to deprotonate. And every time you throw an NaH or KH at something with a proton, you will see hydrogen evolution, basically violent bubbling of your solution, because the H minus is going to combine with an H plus to form hydrogen gas. And those reactions are typically done at very low temperatures, because heat plus a lot of hydrogen would mean combustion or even explosion, and you don't want to have that in a chemistry lab. Okay, so the next thing, well, everything would be awesome if everything is so clear-cut like this. You know, we have a bunch of bases, we have nucleophiles, but we also have molecules that are both. So when we encounter those things become very complicated. So here's a $1 million question. What are the factors that affect the strength of nucleophiles? Because if you have something that's both a base and a nucleophile, you got to decide, you know, is it a strong base? If it's an okay base, you got to ask yourself, well, what about its nucleophilicity? If it's an okay base and an excellent nucleophile, I would choose the nucleophilicity over basicity. And we've learned about determining strong base in Gen Chem. So now I'm going to talk about factors that affect nucleophilicity. Okay, the first thing that comes to mind is charge. Do we like charges? Do we not like charges for a nucleophile? Just take a guess.
Yes.
Yes, we like charges. Why is that?
Because the electrons will favor the nucleus instead of like the electron cloud.
You're absolutely right. So the purpose of a nucleophile, I always draw it this way because I show the pair of electrons that reacts. And the purpose of a nucleophile is basically to attack some sort of, let me redraw this. Is to attack some sort of partial positive carbon, right? And add itself to it. So basically, in order to do that, the nucleophile has to donate a pair of electrons. So between charged and not charged, the charged species would definitely love to donate electrons more because it has more electron density. It has an extra negative charge on it to do reactions. So give you some examples of charges versus uncharged. We can have hydroxy versus water. Of course, OH minus is going to be a stronger nucleophile than water is. And we're going to have also NH2 versus NH3. NH2 has 2 lone pairs of nitrogen, whereas NH3 has only 1. Even though NH3 does act as a nucleophile, it is not nearly as strong as the deprotonated version of it. Also, we have HS minus versus H2S. And the last example I want to give is phenyl phenoxide versus phenol, the alcohol. Okay. Any questions regarding those examples that I gave and the role that charge plays in nucleophilicity? If not, I'm going to move on to the next point. Okay. So the next thing, I think, is going to be the electronegativity. So I've received questions like, how does electronegativity correlate with nucleophilicity? Are they the same thing? Are they different things? Well, they correlate in a way. So let me tell you a dirty and quick rule. So electronegativity. Let's not forget what nucleophiles do. They donate electrons. Electronegativity is all about hoarding electrons. Therefore, what do you think their relationship is? If something is very electronegative, is it good at donating electrons?
No.
It's probably not, right? It has to suck at it. Therefore, so for nucleophiles, at least across the periodic table, higher electronegativity correlates with lower nucleophilicity. For example, let's think about fluorine. Fluorine is a tiny little anion with negative charge. And even though it has a negative charge, it is the most electronegative atom in the entire periodic table. Therefore, compared to I-, it is a very terrible nucleophile. Is it a good base? That's a very tricky question. Is it a good base, Karina?
No.
It's not a good base. Why is it not a good base?
Because like HF is a strong acid, so if it's a strong acid, if the conjugate acid is strong, then the base is weak. So yeah.
The concept is absolutely correct. However, we got to remember that HF is actually a very weak acid. It's incredibly corrosive, but it is a weak acid. Therefore, F- is actually an excellent base. That's a very tricky point because F- can act as both a base and a nucleophile. You got to remember it is a pretty shitty nucleophile, but it's a very excellent base because HF is a very weak acid, even though in order to work with HF, you have to undergo very specific training and wear 3 layers of different protective gears. That I will not go into because I personally don't work with HF. But I do have friends who work with HF, and they say every time they do that, they feel like an astronaut because of the layers of protective gear they would have to wear. Anyway, questions about the trend that we just talked about? If not, I'm going to move on to the next 2 things. And then, if we have more time, I'm going to open the floor for questions. And if no questions come up, I'm going to do a couple of practice problems with you to apply those rules and see how you do. Okay. Electronegativity. And the next thing is solvent, which we've already talked about. Polar Protic solvents favor elimination because they hinder nucleophilicity with H bonding, whereas polar aprotic solvent does not interfere with nucleophilicity because it cannot hydrogen bond. So that was just a recap of what we talked about at the beginning of the class. And then the last thing I want to talk about is sterics. Basically how big or tiny things are, sterics. If things are very big, we call it a big steric interaction. If things are very small, we call it a tiny steric interaction. Anyway, sterics. So sterics also plays a role in determining nucleophilicity. And the trend is that the smaller a nucleophile is, the stronger the nucleophile is. Therefore, I'm going to give you a bunch of examples. If we start with methoxy and move on to T-butoxy, methoxy is the best nucleophile, whereas terbutoxide is the worst due to its size. Imagine you have methoxy, which is very tiny. It's a very concentrated charge on the oxygen, versus terbutoxide, where your concentrated charge can actually be delocalized around the entire molecule. It does not look like, you know, the drawing that we actually do, which is this. You know, in quantum mechanics, we all know that everything is a probability, and imagine this as a huge electron cloud. But for methoxy, it is tiny concentrated electron cloud, and therefore it will be more effective at donating its charge towards an electrophile and initiate the attack and make the final product. Okay, so that was the last point regarding factors that affect nucleophilicity. Any questions? Because this is the end of the lecture part. And if you don't have any questions, we're going to move on to solving a few problems.
I have a quick question.
Yes, then too.
Okay, so what if you have what if your nucleophile, what if the reagent is both a weak nucleophile and base?
It's a weak nucleophile and a weak base.
Yes.
That is a very difficult situation. So good question. So if this factor cannot help you determine what kind of reaction is going to happen,
Yeah.
you look at solvent and the substrate. So
Okay.
if it's in Protic Solvent, it means that it's definitely going to favor substitution reactions. And whether it's substitution 1 or substitution 2, you're going to look at the sterics environment around the substrate. If it's less hindered, probably SN2. If it's very hindered, it's a tertiary carbon, then it's probably SN1.
Okay.
Answer your question? Okay, probably did.
Yes, thank you.
You're welcome. All right. More questions, people?
Yeah, so when you wrote the PHO versus did you write it versus pH? Or?
Let me rewrite it. I understand that I wrote it toward the edge of the board, and actually, let me draw it. This is the PHO minus. I don't know if you can see it. Lights are terrible in my kitchen. I apologize. This is the PHO minus, and with an H, it will be PHOH, which is phenol and alcohol. Okay, cool. Any more questions, people? If not, I'm gonna move on to solving certain problems.
I also was wondering when you wrote that, so under the one with the DMSO, then you had the nitrogen and oxygen with the double bond, but I wasn't redraw it.
You mean the next thing that I drew, like after DMSO?
It was like the molecule with the N, and then it was like 3 of them coming out. Yeah.
This is called DMF, dimethylformamide.
Oh, okay. And then yeah, I'm good with that.
Okay, cool.
And then I have another question. So when you're thinking about, you said like HF would be like a bad nucleophile. I guess if it's without the H, if it's just F, would you still consider it a bad nucleophile? Like,
F is not a nucleophile. HF
okay.
acid. And F minus could be a nucleophile, and it could be an okay nucleophile, I guess, if you're in polar aprotic solvent. Because remember when we just talked about in polar protic solvent, because their F minus is the most electronegative, it's going to attract the most number of H pluses to have hydrogen bonding. Therefore, comparing F minus and I minus, which is the biggest and fluffiest and least electronegative in the halogen sequence, your I minus is going to be a stronger nucleophile due to less hydrogen bonding.
Okay, yeah. Mm-hmm.
Good.
Thank you.
You're welcome. Okay, more questions?
I have a question.
Yes, Emma.
So you said polar protic favors elimination reactions, right?
Polar protic favor, yes, that's what I said.
On Monday, I think we said like it also favors SN1.
SN1, yeah, it does. It does. Sometimes, but it mostly favors elimination reactions.
Oh, okay.
Yeah, they're definitely not wrong. It's just they do favor SN1 reactions compared to SN2 reactions, but mostly it's elimination.
Okay, thanks.
You're welcome.
I have a question.
Yes.
So for polar aprotic, you said that it prefers substitution and that nucleophilicity increases going to like the left in size. So I was just wondering how that connects to the size, because I know that SN1, the size, so it goes to the right, the trend for the size goes to the right, and for SN2 it goes to the left. So how would
Can you repeat what you just said?
Yeah, so for SN1 reactions, we learned that because I minus is a bigger molecule, that's like, it would be better off handling the negative charge than F minus, for example.
Yes.
So stability matters in that case. So for polar aprotic solutions, you said that they prefer substitutions, and then you indicated the relation going from I minus is the least nucleophilus, like the worst nucleophile, and F minus is the best. So how would you connect that to the size, or would you not?
It's a very good question. I think it depends on what kind of solvent you're in. So if you're in a polar aprotic solvent,
Like if you're in polar aprotic, but then you are doing an SN1 reaction.
in polar aprotic solvent, you're doing SN1 reaction. Can you give me an example of that? Or let me make up an example. Probably. Okay. That would probably be easier. Let me imagine an SN1 reaction. Okay. How about this? And you said polar aprotic solvent, so I'm gonna do like DMSO. All right, so cannot do elimination reaction because F minus is a shitty base and DMSO is a polar aprotic solvent. It does not favor elimination reactions at all. So right now we gotta consider what kind of substitution reaction it's gonna do. Is that what you're asking?
Yeah, so like let's say that under there you had one that was the exact same, but it was Cl.
But with
the BR it would be Cl.
Oh, I see what you're talking about. You're asking me about the rate of reaction.
Yeah, because the faster the rate of reaction, the better the reaction, right?
The faster rate of that reaction, so nucleophilicity correlates with rate of reaction. So to measure nucleophilicity, we use the rate of reaction.
Okay.
We correlate positively. Therefore, if by just looking at F minus and CL minus, it might be difficult for you to determine, under this set of conditions, which one is the better nucleophile. But for the rate of reaction, I can tell you that this first one is definitely going to be the faster one. That's experimentally determined, which we cannot do in our heads.
Okay.
So
So in that case, nucleophilicity trumps size.
Yes. I would say if I change this to an I minus, that will be a more difficult question because F is such a small ion, whereas I minus is so big, and the difference should be very big. And in that case, I'm not comfortable telling you, whichever one is the better nucleophile. I don't know which one trumps which. You got to look at experimental data to determine that.
Okay. And the faster the rate of reaction, the better the nucleophilicity. Right?
Yes.
Okay.
Yes.
Thank you.
You're welcome. More questions? I have a bunch of practice problems, and since we have about 10 minutes left, I'm probably just gonna do like 1 or 2. Okay. Coolio. So going to draw. All right. I'm asking you to predict the product and tell me what kind of reaction this is. I don't know if this way it's gonna look better. Yeah, probably does. All right. What's the first thing that we consider when we see a reaction for which we don't know the type and we don't know the product?
The nucleophile.
The nucleophile. Yeah, we can start with the nucleophile. That's cool. So we can start with, let's not call it a nucleophile. Let's call it the attacker because we don't know yet. We don't know if it's a nucleophile or a good base or whatnot. Okay, so look at this. Ethoxide. Is it a good base?
Yeah, it's a strong base.
Yeah, it's a pretty decent base, right? It's pretty strong. What about as a nucleophile?
No.
Is it a good nucleophile or a shitty nucleophile?
Not a good nucleophile.
So remember when we compared methoxy to tarbutoxy, we have a spectrum, right? The bigger the thing attached to the oxygen is, the shittier the nucleophile would be. And ethoxy is not a ethyl is not a big group, but it's definitely not nearly as good as methyl. So I guess it could act as a nucleophile, but it's not like superb. Okay, so we finished considering our attacker. It's a pretty good base, and it's an okay nucleophile. What's next?
Oh, are we still just looking at the reagent?
We're looking at the reagent still. We're done with looking at the ethoxide.
Yeah.
Yeah, we're done looking at that one. But have we determined what reaction is going to happen yet?
No, we haven't.
No, we haven't determined. Yes. So what do you think the next thing is going to be?
I mean, I looked at the configuration.
Mm-hmm.
And so you just see I just saw that it was pericoplanar, like the CL and the H, so that made me think an E2.
Are they pericoplanar?
Well, wait, hold up, because I know if those were in plane, the CL and H they are, but I got confused if it was wedge and a wedge or is it a wedge and dash that's pericoplanar.
Right, so that's a very important question. So we all know that if it looks like this, that is definitely pericoplanar. Sorry, can you see that?
Mm-hmm. Yeah.
If it looks in plane, it's definitely pericoplanar. The question is, if we have the in and out configuration, how do we determine? Okay, so just remember this. If one goes in, one comes out, they're definitely pericoplanar. But if both go in and both come out, they're not.
Oh, okay.
So in this case, are they pericoplanar?
No.
They're not. Can't do it.
So no E2 then.
Yeah, let's not do that because they're not pericoplanar. Okay, so what else? We've ruled out E2 reaction because it's not pericoplanar.
You can look at the substrate. I think it's a tertiary.
Is it a tertiary substrate?
I think secondary.
It's a secondary substrate, which is very annoying because you can't rule out anything in this case.
Since you're using, because the E2O minus would act as a better base than a nucleophile, since you're using it as a base and it's not E2, but it's also not as good of a nucleophile as it is a base, wouldn't it be E1?
Wouldn't it be E1? That's a very interesting question. Okay, so I'm going to add, so right now we've determined that this reaction is hard to classify. So switching up solvent might play a role. So I'm going to give you a solvent in this case and see if that can help us clarify this, because I only gave you half the question to see how far we can go. So there you go, that's your solvent, ETOH. Is it polar protic or polar aprotic?
Protic.
It's polar protic. Okay. Polar protic favors what kind of reaction?
Elimination.
It favors.
SN.
Yes, you're absolutely right. So we've ruled out E2 reaction because in this configuration, of course you can rotate it, but in this configuration, we cannot do an E2 reaction because our leaving group and H are not pericoplanar. So what kind of reaction is this? Karina, I think you nodded just now. What did you say? It's
E1.
Yeah, I agree with you. It's going to be an E1 under this set of conditions. Cool. So I want to look at a different problem because once you've determined the type of reaction, predicting the product would be very straightforward. So any questions regarding this question that we just did? If not, I would like to move on to a different one. And after that one, I'm going to be done with class and you can stay to ask more questions if you would like to. Okay.
Quick question.
Yes, Emma.
Just to clarify, this is a better base than a nucleophile.
It is. I would think so.
I have a question.
Yes, Nestor.
So how did we know that ETO was like at least a decent base? I still kind of get confused like with determining if it's a strong weak base.
So it can be a decent base or a decent nucleophile?
Oh, base.
Decent base. Okay, so let's remember what bases do. So bases take protons.
Mm-hmm.
That's basically what they do. And we try to determine the basicity of something. Basically, we imagine its conjugate acid and determine if it's a strong acid. So what's its conjugate acid?
The ETOH.
ETOH, which is ethanol.
Yeah. I think. Oh, what is it? Oh, you're kind of muffled.
Oh, sorry.
Oh, no, okay. Wait. I did, but then I didn't anymore.
Can you hear me now?
Yeah, now.
Okay, cool. So ETOH is its conjugate acid.
Yeah.
Therefore, it's a weak acid.
Yeah, I'm thinking ETOH is a strong base, so.
Yeah, E2O is a strong base.
Yeah.
Yeah.
Oh, ETOH, right?
ETOH is a weak acid.
Yeah, I thought it was a strong base. Yeah, so weak acid.
Yes. So ETO minus is a strong base.
Oh, okay.
Yeah. We
Oh,
clear?
wait. ETO is also a strong base.
ETOH
Uh-huh.
is a weak acid.
Also, that would mean ETO is going to be the strong base. Okay. All right. Thank you.
You're welcome. You're welcome. All right. So next question, I'm going to quickly go over it and then class dismissed. All right. So this question is going to be a tricky one. It's a homework problem. Therefore, I want to go over it with you guys. Saw that and think it's not very straightforward. No, missing something very important. Okay, so this reaction. We've got this alkyl halide, and we have table salt and water. Basically, you put this thing in salty water and see what happens. What do you think?
So the Na plus would be a spectator ion, and the Cl minus is a good nucleophile, and the H2O is polar protic. So that should help us determine some things.
You're absolutely right. Okay, so let's go over what you just said. Na is spectator ion. We don't care about it. So whatever it does, whatever. And Cl minus, that's a very interesting thing. So we know that it's a weak base because HCl is a strong acid. It's a weak base, therefore, elimination reaction is not very possible. And however, you're in a polar protic solvent. If elimination reactions are not possible, we might be thinking SN1 because, you know, in Samantha's and Sydney's lecture, they mentioned that elimination and SN1 are both preferred in polar protic solvents. Okay, so elimination you can't do. It has to be substitution. Question is, what kind of substitution? And we're leaning towards substitution 1. Okay, so let's see if it's possible. Take a look at this thing. What do you think the first thing is going to happen?
The leaving group, please.
Leaving group leaves. Wonderful. So we're going to have. Okay, what's the next thing? We have the secondary carbocation, which is not very happy because it's secondary. It's not tertiary. Can it be better?
Yes.
How do you do that?
With the methyl shift.
With the methyl shift, which methyl do you want to shift over?
Does it matter?
Nah.
No. Okay, the bottom one. The one at the bottom.
Okay, one on the bottom.
Yeah.
So we're going to do methyl shift. So now this carbon is very happy because it now has a full octet. Which carbon becomes unhappy? It's this carbon. Now we have to put a positive charge on it. And then what's the next thing that's going to happen?
Cl minus attacks.
Cl minus is going to come in and attack, and then we're going to end up with our product that looks like this. Okay, the tricky part was the methyl shift. To be honest, the first time I did this question on my own, before looking at the answer key, I got it wrong because I didn't think of the methyl shift. So this is just a reminder, you know, when you see a secondary carbocation, definitely look for hydrogen shift or methyl shift, because if that can make it a better carbocation, it will. Okay, so hey, I'm right on time, 1 minute away from the end of class. So I'm gonna stick around for a little bit to answer questions if you have any. The rest of you, if you don't have any questions, feel free to leave, and I wish you a happy weekend.